Good afternoon, everyone. It's my extreme pleasure to welcome Tamara Munzner from the University of British Columbia to give our tech talk today. I've known Tamara since she was at Stanford and I was at Park, and you know how these things work, social networks and everything. And she is also an alum of Building 43, which you lived here in a previous existence at SGI. I wanted to remind everyone to keep confidential Google questions to after the talk so they won't end up on video.google.com, which is considered a bad thing. So please save those questions, and when you ask your questions, either say them extremely loudly or we'll have Tamara remember to repeat them. So let me turn it over to Tamara. Welcome.
Okay, thanks, Dan. So today I'm going to talk about 15 views of a node-link graph, an infovis portfolio. So let me start out by defining a few of my terms. Node-link graph, this is a very common idea in computer science. All I mean is any kind of a abstraction where it's useful to think of data as nodes connected by edges. And of course, trees are a special case of graphs where you've got a hierarchical structure, so there's no cycles in the graph. Now, what do I mean by information visualization? I'm going to typically abbreviate this as infovis for the talk to save myself some syllables. Any kind of a visual representation of an abstract data set. Now, that's a pretty general way to think about something, and of course, that did not originate with computers. People have been making diagrams to help them think for a long time. What's relatively new, say in the past 15 years or so, is making these interactive with the computer, and a lot of the examples that I'll show allow interactivity to give you more power than you could from just static pictures alone. And also there's some idea that we're not just making pretty pictures in a vacuum for beauty alone, we're making them to help people get some particular job done, either faster or more effectively. So there's a lot I could say about how to design these kinds of infovis interface, and I will say very little today. Most of what I'll be doing is showing you a gallery of examples to get you thinking about what the design space is like. And rather than ranting for 6 hours or 18 hours about how to do these, which I'd be happy to do some other time, I'll start with just really a single slide to give you one of the ideas behind what are some of the things that makes this tricky. So if we are using marks to have some kind of meaning for a person, there are ways we can do this that actually can communicate information through your perceptual system. So you've got, say, some mark on a page or in 3D space. Well, the position of the mark could mean something. We could encode the information using color, or the size, or the shape, or the orientation. There's a lot of these ways to do it. I'll call these visual channels. And I'll call a general idea of how to visually represent our data visual encoding. And as the talk goes on, I'll talk about the particular visual encoding choices in these 15 examples. But some of the reasons it's not so easy to just say, well, we've got all these ways to encode information. And so surely if we've got, say, just across the top, I've got 5 different ways to encode information. So does that mean I can easily just encode any kind of a 5-dimensional data set so that you can get it? Unfortunately, the answer is it's not quite so easy. These are not all orthogonal channels in the way that the human brain actually interprets visual information. So some of these are quite nicely separable in your brain. So for example, on the left, it's really easy to see that there's 2 groups of dots, one on the top and on the bottom, so we're encoding by position. And it's really easy to see that there's green dots versus black dots. So those are 2 highly separable visual encodings, no trickiness here. But as we go across towards the right, your ability to disentangle 2 separate variables gets less facile. So for example, if we go further over to the right where we've got X size and Y size, if you stare at that and concentrate, you can try and pick out groups that are based on whether or not something is wide in X or tall in Y. But if you don't concentrate hard, it's easy just to perceive that as an area. You just tend to perceive, oh, this is how large the thing is. So you've got X and Y size starting to collapse into each other. The example on the far right is a pathological example. Even if you concentrate, you can't actually group these dots into clumps based on their position along the axis from red to green in color space and their position along the axis from yellow to blue in color space. You're just perceiving a color. You're not able to actually separate those out even with concentration. So we go from, you can separate these out even in fact without a lot of concentration at all to you can't at all. There's a lot more of the theory of how to do this kind of visualization design that I won't get into. This is just enough to give you a tiny little taste of some of these issues in the fact that the human eye is not a camera, the human brain is not a perfect memory recorder, and we're designing for the specific perceptual systems of people. So I'm going to start out in this walk through the design space with some relatively traditional representations of graphs, go on to some less traditional ones, and then move on and focus on trees. And there's a whole class of techniques for interacting with them that's called focus plus context, and give some more examples there. And then wrap up quickly at the end. Feel free to interrupt with questions in the middle if you like. So I'm going to start with an example. I should have called this example 0, because in some sense it's not a visualization example at all. It's simply a listing of edges. Now, I'm putting this up, and it's not just a straw man, because I want to make a point about when the perceptual system helps you and when it doesn't. So the book Gödel Bach is about a multitude of computer science topics and how they all relate to each other, and it's a tour de force. And he actually does, for example, connect infinity to a lot of other topics. And if I ask you to read off from this list of things, well, what's connected to infinity? You have to go along, store off the fact that the halting problem is connected to infinity, keep that in a little mental buffer. As you continue going on, you see, Lewis Carroll's also connected into infinity. And then you continue to see, decision procedures are connected to the halting problem. And what you're doing is you're using a lot of memory, and you're having to do specific cognitive processing to reach the conclusion of what's in the nearby vicinity of infinity. So what's nice about this is it's dead easy to create, and what's horrendous about this is it's actually requiring a lot of work for the human, and we're not doing any of this exploiting of the perceptual system. That is what's the hallmark of visualization. So if you are allowed to draw a picture of these things, you can read the answer off the graph. So that might sound simple, but what's actually happening is interesting from a point of view of you're using your perceptual system. When I see a link between infinity and paradoxes, then that gets translated into the knowledge that there's a relationship. And then I can read off when there's another link connecting paradoxes to Epimenides. I can now avoid doing cognitive processing. I'm swapping in perception. So it's making an external source of memory where your eyes can move around very quickly, and you can get information without having to do a lot of memorization or cognitive processing. Now, so what are some ways we can get these pictures? Well, if you're maniacal, as Hofstadter arguably was, you can hand draw your pictures. So this is a page from the book of the semantic network in Gödel Bach. Now, there are some strengths about this hand-drawn picture. One is it's got very high, what I'll call information density. So talking about the ratio of the marks to the white space. Of course, if you go too high, all you have is clutter. Too low, and you're wasting a lot of white space, and typically pixels are a precious resource. But this is actually very nicely done, and there's a lot of subtleties here. I think I'll use the mouse because I'm not tall enough to reach. So although it's probably hard to see, except from the very front of the room, this book being about Gödel Bach, there's Gödel on top, I believe Escher and Bach are a central triangle. There's the node right in the center that has to do with all the connections that go through all three. Notice how the edges are carefully routed around the nodes to avoid running through their centers. There's even visual puns, like this node is called jumping out of the system and the edge goes to nowhere. So it would certainly be hard to make a completely automatic drawing that had all of these subtleties. But of course, this probably took him hours, if not days, to create. What if, of course, instead of 300 nodes, you had 100,000 nodes and they were changing over time? Clearly, hand drawing is not going to save the day. So I took the same data set and I put it into one of the early successful graph drawing systems. This was DOT, a system from AT&T as part of the GraphViz package. So one of the central problems in graph drawing is, given this assemblage of nodes and edges, which is just a purely topological structure, how do you make a visual representation for it? That is, let's compute the position for the nodes and somehow route the edges in between them, either as straight lines or in this case as nice spline curves. And that's the automatic problem of graph drawing. Now, the strengths of this is that it's very fast. This took about a second. Notice how there are some aspects of the careful hand-drawn picture that are preserved. These edges here are actually routed around all the nodes. None of these spline edges pass through a node. Now, the downside is you can't actually read any of the labels, even the ones of you in the very front. The scale of the size of the entire graph compared to the size of the text labels in the nodes is much greater than in the other one. In the other one, you had a fighting chance at reading the labels, so you actually had greater information density. This one's going to require a lot more navigation way in to read the nodes, and then zooming out to see the structure of the graph as a whole. So one of the big problems in graph drawing is how can we do a better and better job of the technical aspects of trying to make it so that you can see as much structure and detail as possible. And of course, ultimately also, is the picture that you're drawing actually properly tuned for the job they're trying to do with that data set? And so we'll be looking at more points in this design space. So why is this hard? Well, people have developed a set of metrics to try to encode some kind of aesthetic criteria that people use when they look at a graph and try to make sense of it. So for example, one of the typical aesthetic criteria is that you want to minimize a bunch of things like crossings of lines, or the total amount of area you use, or the number of curves or bends. You also want to maximize some things. In this case, angular resolution is so that if you look at the graph from far away, you can distinguish that those two lines are separate as opposed to drawn right on top of each other. Or if there's symmetry in the graph, try and have a layout that shows that. Now, what makes life rough is that most of these criteria, each one of them is NP hard. Most of them have been proved that long ago. So what's interesting is that we know that we're not just going to have some brute force computation where we'll find an optimal answer and go home and be done. For a long time yet, we'll be doing heuristics to try to find something reasonable. And it's likely that these heuristics may well depend on the specifics of the problem that you're trying to solve. Just to make life even worse, many of these criteria are in fact mutually incompatible. Even with a tiny graph of 4 nodes, already you can see that these criteria of symmetry and edge crossings give you different optimal layouts. So there's been quite a bit of work both on trying to formalize the ideas of how can you understand a picture that's encoded as a graph, and what are the computational complexity of these various approaches. So one thing that a lot of people have tried doing, and in fact a lot of wheels have been reinvented, is something I'll call in the general category of force-directed placement. So you've got this physical analogy that your nodes are like magnets that are repelling each other, but your edges are like springs drawing them together. And often you'll start either from some random position or maybe some more carefully computed initial position, and then you run the system to convergence. And what you get is the idea that you're trying to have the geometry of the final placement of the nodes on the page be roughly correlated to the graph theoretic distance, the number of hops it is from one node to the other in the graph. So here's an example for a very small graph of just starting at some initial position and gradually evolving into some layout. Now, there have been many, many different mathematical approaches to doing this. The nice thing about this approach is you can throw a lot of heavy lifting mathematical infrastructure at this to try to get some traction for this problem. So the strength is it's easy to explain it. There's a lot of different ways to try to tackle it mathematically. But the fundamental weakness is that you've got this n-body problem. And fundamentally, you're saying what's the forces on one node compared to all the other nodes. You have to do this multiple times until you converge. So you end up with an n-cubed algorithm, and that's simply not going to scale. So one approach people have done more recently, say in the last 5 to 10 years, is let's not just tackle the entire graph at once. Let's chop it up into pieces, hopefully in some kind of a clever way, and have some kind of a multi-level structure on the graph where we can try to solve an easier problem, use that to springboard to solve the harder problem, and so on with refinement until we have some way to lay out the graph as a whole. So there have been a bunch of approaches to this multi-level layout, and one that I'm enthusiastic because we've been working on it lately, this just got into the journal TVCG a couple weeks ago, is to try to chop this up by topological features. So the idea is we've got a bunch of specialized algorithms that are good at, say, drawing trees or drawing clusters or drawing near trees or finding structure that actually is meaningful in terms of the way people think about it, like chop it up into biconnected components. So the topo layout approach says we'll chop up the graph into components based on these topological features, use algorithms that are well-tuned for the particular feature to lay it out. There's some special sauce at the end, which is try to make sure that then the final drawing, when you put all these pieces together, is refined so that you have good information density, which tends to always be one of the hard problems. So I'm not going to have time to go into detail on this since I'm kind of whipping through many things in this brief tour of infovis and graph drawing. But you can look at data sets like, say, websites or the structure of the internet router backbone and get better results than in previous methods that didn't try to take this topological structure into account. Now, the strength and weakness of this algorithm is pretty much the same. If the features we detect and lay out well are present in the graph, then we do great. If those features aren't present, then we're not going to do well. Or there's even a more subtle thing, which is that if those features don't correspond to the way that the user actually needs to think about that graph to get their job done, then you could argue that it might even actively mislead. In the red.
Are those two pictures of the same graph or different?
The question was, are those the same graph or different? And the answer is a different graph. The graph on the left is the structure of a website. The graph on the right is the structure of an internet router backbone. That Bill Cheswick's been doing internet tomography to try to mine that structure. So far I've been talking about a static problem, which is you're given a graph and then you have to draw it. But of course, a lot of the interesting data sets have dynamic data where over time the structure of that graph changes. And there's an interesting problem, which is that you want to minimize the unnecessary changes in the layout. So you want to have as little change as possible as the graph changes visually, yet the actual structure is changing, and so the drawing should always reflect that current structure. But it's possible that if you don't take into account a careful analysis of how the change could happen, you could have a lot of unnecessary visual change. Question over there.
If for each of the metrics that you mentioned, like for instance symmetry, or in this case like that when they change, they need to change in a particular way. Have there been user studies which say that it's really something that people care about, or is it something that mathematically it's elegant, so we just go down this path?
So the question was, for these metrics I talk about, have they been validated by user studies, or are they just mathematically elegant, but we're not quite sure whether they match? So the short answer is most of them have been validated by user studies, and of course, like all user studies, then you can start to quibble about whether you believe those particular ones or whether they're capturing the full story. But for example, Helen Purchase and Colin Ware are two researchers who've done a fair amount of trying to go from intuition to formalization of a metric to user studies that say which of these metrics actually have the most impact in terms of users' perception of the graph structure. Ms. Sue is another one who's done a fair amount of that. So yes, they've actually been working on validating these. Of course, going back to that previous slide about multi-level hierarchies, one thing we're right in the middle of working on, which I'm really excited about, is trying to take some of these metrics and generalize them to do something useful at the multi-level structure, because all the work so far has been at a single level. So there's a lot left to do on that, but a lot of that has been validated back to actual user studies. So for this question about dynamic graphs, there's this question about how to minimize unnecessary changes. So let's go ahead and look at a video. This is work that was done at Berkeley a couple years ago. And I'm actually going to talk over this instead of using their voiceover. So here we've got a graph that's changing over time. And right now they're actually, I believe, just monitoring a Nutella network. So one aspect is there's whether the graph itself is dynamically changing, which we saw at the middle, and then the ability to interact with the graph. And in this case, it's a radial layout that's based on some idea of a current focus node. The user can change which node is the focus, and then the graph is moving accordingly. I'm going to move this down a little bit so we can see the top of the screen. Now, so what you're seeing here is the navigation. And now what they're going to talk about, again, I want to see the very top of the screen, is specific ways of doing that animation that's easier or harder to follow. So if you just interpolate the position of the nodes rectangularly, what you'll notice is that you get this kind of collapsing into the middle effect with this graph, and it's relatively hard to follow. If instead you interpolate by moving things around in polar coordinates instead of the rectangular coordinates so they roughly stay at the radial level that they'll be, it's easier to follow. Here what they're showing is that if you have no constraints at all on maintaining sibling orderings, when you move around, you again get a lot of unnecessary motion in the graph. By saying instead, let's impose a constraint, enforce that sibling ordering is maintained, it's easier to see what's happening as the graph moves. There's another constraint based on some of the physics of Disney animation, which is instead of just moving linearly in time, you start out slowly and then go more quickly. So this is enough at least to give you some sense of the fact that by imposing some constraints, you can actually make these kinds of motions easier to follow visually. So I'm not going to show the whole video, but it's enough to give you a sense. So one thing that that approach did well at was simply by saying, let's interpolate in polar instead of rectangular coordinates and have some constraints on maintaining the neighbor order, it's actually easier to follow the animations. And in general, the idea that if you've got two states and you want to go from one state to the other, there's one of the conventional wisdoms in infovis is you definitely want to have some kind of a smoothly interpolated animated transition instead of just a jump cut, so that you don't have to reacquire some target of interest in one picture and see where it went to in the other. You can just track it as it moves along. So there's typically been a lot of effort put into what are the right kinds of animated transitions. So this approach actually did succeed in having smoother transitions. One of the weaknesses, though, is that it doesn't scale up to larger data sets. I'll be talking later on about some approaches that actually try to take into account what if instead of having hundreds of nodes, you had tens of thousands or hundreds of thousands or millions. There's a bunch more typically graphics infrastructure you need to do under the hood to make that kind of a system scale up. This one was pretty limited to several hundred points. One thing I'll note is that the dynamic problem is much harder than the static problem. That's pretty much the state of the art in dynamic graph layout, although people have made a lot of strides lately in trying to scale up static layout to much larger data sets, getting up into the hundreds of thousands. So here's a different approach. And this is an approach for what's basically visual debugging. So this was a system designed for a small number of people, of computational linguists, who were taking an entire online dictionary and making a semantic network where the nodes were English words and the links are these two words were used together in some dictionary entry sentence that was a definition. And what they were trying to do is determine whether or not their networks for creating and using the semantic network matched the intuition of an English speaker. So it was really debugging their own algorithms, not intended for end users, but really a kind of very specialized kind of visual debugging. And one of the design principles we used when designing the system was, I mentioned how important information density is, that you really wanted to use all of your screen space effectively. So that is an important principle. So one of the things we said in an early version was, well, let's make sure that if we have a certain amount of room to draw a word, we'll compute what font we can fit, and then we'll use the maximum possible font. When we actually watched the linguists try to use this system, we found that they were misjudging something important, which was that they thought that longer words were less important than shorter words because the shorter words were drawn bigger, right? So there tends to be a bunch of trade-offs in the design space, and often they bite you in the ankle only when you actually see your intended users using it, because of course you, the designer, knew what you had in mind. So typically there's a lot of iterative design in systems like this. So what we found was that it was really important that the visual salience, that is the visual weight of something, should match this idea of computational importance that we were trying to convey. So in the final version of the system, we made sure that words that were equally computationally important were drawn of equal size, so we didn't just have this idea that to draw things as big as possible if we've got the pixels. And then we found that that was a reasonable compromise that had both information density and the visual salience matching. In the orange?
See any effect about the color?
So the question is, did we see any effect about the color? We're actually using, this is a system where we're using color coding in some very specific ways that are interactively changing over time as you interact with the system.
I'm sorry, the perception that a different colored word would have a different...
The question is whether a different colored word would have a different perception. One thing we did was actually buy into some of the literature, which is that it gets fairly hard to read colored text, and that it's a lot more effective to have text that's either, say, all black or all white against a colored background. So we switched to something where the color coding was that you had these blocks containing the words rather than trying to actually draw the words in different colors. to get the maximum contrast for legibility.
So when you were doing your visual salience analysis of this, were you taking into account just the text labels for all the features? So what's been visually salient that you've seen like that?
So Dan asked, in this visual salience analysis, did you take into account just the text or all the features? What's visually salient? As if you were an audience plant, going on to my next point, which is some issues about visual salience and what did we do in this design that was different than some others. So hopefully I'll answer this question within the next 2 slides. So I mentioned that one of the traditional metrics in graph drawing is avoiding too many crossings of edges. One of the reasons we do that is that there is some visual ambiguity and salience of the wrong things in the design. So in particular, it's not obvious here, is A going to C and B happen to be in the way? Or is A going to B and B going to C? There's actually 5 or 6 possibilities here, and there is an ambiguity, so there's confusion. This one is slightly more subtle. There's not an ambiguity here, but the important thing is that A is connected to C and B is connected to D. The place that your eyes immediately go to when you see this picture is the X in the middle. So the X is a salient visual artifact that draws your eye that doesn't actually have meaning. So that's another one of the reasons why people try to avoid edge crossings, is they're overloading your perceptual system with stuff that's not so important. So fundamentally, the problem is you see things that are confusing or that misdirect your visual attention. In this system, what we decided to do was create a perceptual layering effect, where when you interacted with the system, what you would see was that some small set of words and edges would be highlighted. And this highlighting was actually based a combination of increased saturation and brightness and size with line width. And then this layering effect was effective in the sense that you'd see a foreground layer and a background layer. And even though there are quite a few crossing lines that you can see in this picture here, once there's a visual foreground layer, it's fairly clear that this line is connecting up and going off that way, and the fact that a lot of other lines are crossing it is not a problem perceptually speaking. So we basically said if you consider interaction to be a first-class primitive, and you're allowed to interact as a fundamental way that you deal with the system, then you can see different snapshots being highlighted and avoid perceiving the false attachments and not have to have the spatial layout to do all the work. I'll show you a short video to get a sense of what that system looks like in action. So here's an example where what's been selected is a small, again, I think I'll just narrate over this as it goes. What's been selected is pretty obvious as a visual foreground layer. And you can see that there's a small number of these. What you'll also notice is that there's some specific kinds of zooming where when you're far out, one word is large and the rest are small. As you actually get to the point where you've got more room available as you're zooming in, it's not quite a linear zooming in to the point where you can read all the lines. And then there's a lot of, again, interaction where you can flip through and quickly get a sense of where one word connects with all the other words. And specifically, I'll now bring up the movie right after this, which is showing more of the flipping through. So here's the idea that you could either flip through various pathways. In this case, the pathways were these paths that had been computed through the system. There's going into the more detail about the exact interface approach using a little scroll wheel on a mouse. What's interesting here then is you can either flip through the pathways or through entire definitions all at once, which correspond to one of these rectangular blocks. That's starting right about now. So the key thing is that you actually are getting this perceptual layering. In this case, they were going through all the connections to particular words. So that's enough of that to at least give you a flavor of it. So what's interesting about this system is that its strength and its weakness are the same thing. It's very highly specialized. So I mentioned this was designed for a small group of computational linguists, And the methods that they used before to try to understand whether or not their algorithm's working involved bringing up a vast number of windows and flipping around in between them, and they were having to remember a bunch of things in their head and compare the memory of something to what they saw on the screen in front of them. One of the things the system was designed for was to try to have all the information they needed more available in one space at once and use interaction rather than having to just use the memory of what you had seen before. So it was much, much better than any off-the-shelf system for doing that. Yet it took a designer, me, quite a bit of time to actually design and build that system. So information visualization is at the point where building these kinds of highly targeted systems where it's really clear whether you've helped or not because their task is really crisp and concrete is one of the modes that this field is in now, so that we can then learn from that, evaluate whether it worked, and build a richer set of design principles about how to do this, to get to the point where we as a field can kind of give you a cookbook which says, here's your data set, here's your user, here's your task, here's some suggestions about what to do. You have to start by exploring the design space before you can have that kind of prescriptive cookbook advice. So even though that kind of custom system is really expensive, there's some value in trying to choose some case studies and learn from them now. Some things that work is that we actually did succeed in the final version of having a nice trade-off between the information density and the visual salience of making sure that they drew the right conclusions from what they were seeing. And this perceptual layering approach did end up working out where we had a bunch of visual channels all redundantly enforcing this idea that there's a foreground and a background layer. So let me move on to some less traditional representations of graphs and trees. So typically, if I told you about some little hierarchical structure of 6 or 7 nodes and I asked you to sketch it on a napkin, you'd probably draw a picture like the one that's on the left, where you've got this node link graph where you're saying that there's a parent-child relationship by drawing a line in between them. But you could also use another visual vocabulary item for doing that. You could say, well, I can have things contained within. So containment instead of connection. Now, what are the pros and cons of this? An approach called tree maps uses containment instead of connection to show this structure. If you really care about the topological structure of exactly how the parent and children relate, then this connection system that most people use is probably the right way to go. But if you've got attributes at the leaf nodes or the interior nodes of the graph that you want to try to encode visually, you can actually do that here. Here we can see that D is much larger than C, say, and that F is larger than E. And you're seeing that with your perceptual system rather than having to read a number and think about it and cognitively compare this number 3 to 10. So we're always trying to exploit perception here. So typically that attribute might be something like the size, if it's a file-in-a-file system, or the performance of a stock. So this tree map approach is really effective at showing outliers in this attribute that you're encoding. Say through size, you could also encode things through color. The map of the market is one of the applications of infovis in the real world that most people have actually seen. Tree maps were initially invented almost 15 years ago, but they've been percolating in tech transfer from infovis into the mass market in the past few years. Now, to show you how you can take this idea and then try to refine it, one of the problems is there is some structure that's clear on the top. It's a lot harder to see if we just use black and white to understand the relationships of the parents and the children. We're essentially losing a lot of the internal hierarchical structure and just focused on the leaves here. So one of the ways to try to make that structure more visually apparent without using up another one of these visual channels of color is this approach where you're assigning these areas to basically virtual bumps. So you're simulating the shading as if this were a bumpy surface, and you're more able to see the hierarchical structure in this picture without using up color coding. Now, what's nice about this approach is just by manipulating the relative sizes of these virtual bumps, you can either be focused on the really low-level structure or smoothly change to be more focused on the higher-level structure just by relating the size of the bumps to each other. So tree maps were originally proposed by Johnson and Schneiderman, and this refinement was proposed by Fenwick and Van de Wettering. So what's nice about that is it's not getting rid of the fundamental nice attribute of tree maps, which is try to show this attribute information, but it adds back a little bit more of the topological structure. And then it frees up color to be used for something else, like some categorical information about the kinds of node attributes you have. Now still, if you are actually trying to understand topological structure, you would just use the more traditional formulation. So if you're mostly focused on attributes, but there's a little bit of topological structure you'd like to see, this is actually an improvement. So another approach that's been proposed by several people is, well, sometimes instead of actually seeing all the details of the graph structure, you want to take a bigger view. So if you go from the idea of having a node link graph that you lay out, and then take away, after you do the layout, take away your edges. Think about where you've got your nodes implanted in the plane and treat that as a density function, and then try to wrap a skin over on top of it, and you get this virtual landscape or a terrain. This example across the top is actually using gene expression data where you start out with just a table full of numbers about the amount of influence that one, say, gene or protein has on another. You threshold that to get some kind of weighted edge structure, and do that, use that for your graph layout and then for your terrain. The example on the bottom was a corpus of a week's worth of news stories and trying to give people some sense of this terrain of news of what were the most covered topics that week. So this was originally proposed from some folks at Pacific Northwest National Labs up in the Pacific Northwest. Now, what's interesting about this approach is it's one of these models that's very intuitive. People are used to thinking about terrains, especially people in the general public kind of will latch onto this view and say, aha, it's hills, I get hills. So people tend to find it fairly evocative. I argue it's probably fairly good for things like an overview. A lot of the methods that have been proposed using this allow you to then go in and explore maybe in a little more detail because you're losing a bunch of the information when you go off to make these terrains. So I'm personally interested in trying to evaluate when exactly people might get some benefit from using this, or is it just that they find it sexy as opposed to actually useful? Question in gray.
It seems like in order to make sense of that, you need to have a lot of experience looking at smaller graphs that are used with the same layout or eventually wrapping the skin on them. So if you're used to looking at trees or you're used to looking at the weighted edges of the springs, it makes sense, but if you wrap skin over a very sparse map layout graph, it might not work.
So the question was, do you have to be familiar with that family of graphs before that kind of terrain layout will do you any good? Now, most of the people proposing this kind of approach would say no. You don't have to be. In particular, so this gets back to this question of, does it matter exactly where the hills are in relation to each other, or simply that there are hills and that some are tall? So I'd argue that really what this approach is going to get you is, oh, look, there's a couple tall hills. What are those labels? And if the clustering is actually reliable, that is, if you, instead of having a random seed where you have a whole different set of hills every time, if you can reliably say, yes, the clustering is legitimate and actually reflects the structure of the data set, then maybe they're going to learn something effective. So one of these papers is actually about the idea of making sure that you do get reliable clustering so that it's meaningful, which I think made this technique a little more effective. So their argument is actually, so what I agree with in the last part of your question was, well, what if you had a sparse and bad layout? Then probably this wouldn't be helpful. I definitely agree with that. This is probably something that's more suited for showing you clusters than for showing you the exact subtleties of the layout. I also caution that it's probably a little dangerous in the sense that if you've taken a bunch of samples and then you're interpolating them and then people start drawing conclusions about this interpolated data, you have to be careful that they're not drawing conclusions about artifacts, about the idea that, oh, maybe there's actually a gradual slope here when in fact you don't know. You're just interpolating between two things. So that's typically always something you have to worry about is, are they drawing conclusions from an artifact of your visual representation or something that's actually truly present there in the data? So here's another approach. Again, you would typically draw a picture of a graph if you were given a little one on a napkin with this connection between the nodes in the graph. Another way to visually represent that is in a matrix where one side of the matrix is all the nodes in the graph, Same for the other side. And then in the cell where they meet, if there is an edge between them, then you darken that cell. In this case, they've actually got a 2-level color coding of green versus red edges here. Now, there's some interesting aspects to this approach. So it's certainly true that as you get a larger and larger graph, if you're not careful, you get more and more of the kind of ball of yarn or tangle of spaghetti problem where you just have this thicket of edges and nodes and it's really hard to understand structure. So in some sense, the matrix approach is an end run around the problem of how do you reasonably lay out a graph in a way that shows some kind of structure. This particular project by Frank Van Ham was trying to take a large-scale software project and show the developers something about the structure. In this case, for example, was a call in the specification, or did it creep into the implementation without actually having been desired in the specification? That's sort of showing in red there. Now, what makes this a multi-level project is the argument that matrices are nice if what you want to do is have some kind of multi-level structure where you can either have a very coarse level view, or you could zoom in, say, to one of these and see a more fine level view. And you can do that within exactly the same amount of room. You've got this kind of stable structure for doing this kind of recursive zooming across the levels of the graph. In contrast, you can imagine that if you wanted to zoom in to something like that force-directed graph in the middle, it can get tricky to know exactly what's the area of the screen you'll need to do that. So there's some nice aspects of being able to just look at these matrix blocks. And one of the things that this project did well was it actually did show developers who'd spent a lot of time in their code base some things that they did not already know by looking at this visualization. So literally they had spent months working with this and discovered some new things about some problems between the implementation and the spec. Now, there's a really fundamental issue here, which is only some tasks are well supported by this kind of a matrix view. So, for example, a recent paper by Goniam and Fiquet tried to do user studies about what tasks can you do with a matrix view and what tasks do you really need the more traditional node link view for. So when they started on characterizing the kinds of things you can do with these views. So let's now move on to some more interactive systems. And we're going to be focusing specifically on trees, although I'm going to sneak a little bit of gene sequences in there right at the end. And we're going to talk about this class of techniques called focus plus context. So that's a buzzword from the infovis literature, which really means this idea that we're trying to combine information about an overview with information about details into some single integrated view. So that's as opposed to something like having a single view where you can navigate your camera around freely. So sometimes you're very zoomed in, other times you might be much more zoomed out. And the problem with that kind of a view is you have to remember what it looked like before. And that kind of using your memory instead of just being able to read the answer off is typically the kind of thing that we're trying to get around with visualization. Or you could imagine, well, what if you had multiple views? It's very common in something like Photoshop where you've got your main view and then a little overview window showing you roughly where you are. So that helps a little bit, but there's still, the conjecture is, some cognitive load in trying to correlate between those two views. So the question is, can you try to integrate information into one view? Will that make things easier for the person? So one of the systems, this is by Pleasant et al. From Maryland, it's called Space Tree, and it's a very interaction-based system. So it's saying it's true that there might be a very large data set that you're trying to explore, but what we're trying to show you is just a small set of that you're looking at once, but give you some sense of where you are in relation to the whole. So let me show you a demo of that to get a sense of what that's about. And I will shrink this view a bit. So right now, we're looking at the very top level. This is actually a node link representing relationships between species. And when you click on one versus another, you're really focused on the path from your current choice back to the roof. Sorry, back to the root. So let's zoom into the mollusks. So the thing to notice is you don't necessarily see everything at once, And you have some kinds of hints about things that are likely to be large. For example, the little glyph by the chordates, things with backbones, is pretty large. So this is showing you a fairly small set at once, but it's making it really easy always to see where you are in relation to the root of the graph. You can imagine that if it were drawing out the whole thing, this is 200,000 nodes, it would be quite hard to keep track of where you are in relation to the root because things would be very, 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 very spread out. So it's allowing you to interact and pick a small set at once to see. So the strengths is that, again, coming back to this theme that as you move through the graph, you typically want animated transitions between the different states to be able to track things. But if the task you're doing only requires seeing a small amount of information, especially paths up towards the root, then this is going to be a nice tool. If you have to see a bigger picture, then you're actually seeing only a small fraction of the information. Another approach that was proposed by Lamping et al., and I believe Lamping's now here at Google, at last I checked, is trying to use some of the mathematics of hyperbolic geometry to give you this fisheye-like effect. The idea being that, again, if you just draw a completely traditional drawing of the tree, it's going to be very, very spread out. In particular, it's going to require an exponential amount of space as the number of nodes in your tree grows to draw that picture. What you want is this carefully chosen distortion to say that some parts of the tree are drawn large and others around the fringe are drawn small. So this is actually inspired by the same kind of hyperbolic geometry that Escher used in some of his pictures, where technically, it's a whole other talk to get into the mathematics of this, but grab me afterwards if you care, because it's really nifty. So you can actually move things around on a hyperboloid and project down into the plane to get this kind of an effect where some things are large, things are small around the periphery. And the key thing from the point of view of interacting is that you can, by selecting a node that's currently far away and small and dragging it back towards the center, you can then see that that becomes big, and what used to be big gets pushed off towards the periphery. So this is using a single focus. So there's essentially one thing that's large in the middle, and then things all fall off around that. So this is using the mathematics of 2D hyperbolic geometry. Let me actually just show you a quick demo to get a sense of what that's about. So this was something, I've been working with a lot of biologists, so I tend to pick examples lately looking at relationships between species. So this is another relationship between species one. Notice how we're actually a little bit cut off here. Let me zoom down. This is in a rough oval shape, but you can pick what's going to be large, and then other things get pushed off towards the edge, and we can go back down to the original root node. So this kind of a fisheye-like effect is showing you a larger neighborhood of the graph than you could see with a purely traditional view. And you notice how you get some information of what is a possibly fruitful direction to go in versus a place where there's nothing there at all. So we can see that there is some structure here that we can then zoom into to see in more detail. Whereas we can know that right over here, in fact, there's nothing and there's no need to explore there anymore. So what's nice is that this can actually start scaling up beyond just hundreds of nodes. This works well even with graphs of over 10,000 nodes. There's a couple caveats. One is any kind of these methods where you're trying to do some kind of distortion to see more things smushed around something, you've got to be careful. If you're doing any task where a judgment of distance is important, then you don't want to use this whole class of methods, because we're actually changing the distance as you interact to try to show you more things at once. And it is possible to get lost and lose track of where the root is if the graph gets big enough. Some slightly later work that was from my own thesis work again, the H3 system is trying to use the mathematics of 3D hyperbolic geometry instead of 2D hyperbolic geometry to try to fit more information in at once and do better on the information density. So I'll briefly show you a little bit of a video of this system in action, or you can download it and play with it off the website. It's a free system. So in this one, we are moving around, and there's some similarities to the 2D system in the sense that they both have a single focus. In this case, it's at the center of a ball rather than the surface of a disk. And it's got that same property where you can move things very far away and they'll get small, or whatever you move towards the center will be drawn large. And in this kind of a system, simply by, you can either freely drag around, or if you click on a node, like we did just here, it'll move towards the center with all of its ancestors on the left and its descendants on the right. So the aspect of this where we're seeing a little more information than in the 2D case is that the aggregate information on the fringes about, say, there's stuff here and there's no stuff elsewhere, you're getting to see about more nodes at once. Let me flip to the next piece of the movie to show you another aspect of this, which is, you'll notice I said this was a system for graphs, but what I'm showing you now is a spanning tree. So the idea is that there's a lot of trees where showing a spanning tree can be a useful way to think about it. If you drew everything, this is basically the what not to do picture, it's a mess, right? This is an example of actually an entire website where if you try to show all the interconnections, it's very hard to understand what's going on. What this system was built for was allowing you to say, don't just draw everything. Instead, select some node in particular, and then draw the non-tree links, either incoming or outgoing, just for that node, and it allows you to do a more fine-grained investigation and understand some of that structure. So you're looking at it piece by piece instead of being able to see all of it at once. But that's basically a way to give you traction. Now the argument is, when could you use these kind of spanning tree-based methods to look at a general graph? And the answer I give in this paper is, well, a lot of tasks actually have some idea that there's hierarchical structure even in a very dense graph. Like in this case, websites are dense. They're not just trees. But there's a mental model where you can say that based on the directory structure of the URL, I can infer a hierarchical structure that actually is probably what the webmaster was using to think about. Similarly, you could do computations to try to show structure of some software call graphs where you're doing a combination of static and runtime analysis to try to find what's a good spanning tree. It's actually going to be helpful rather than misleading. So this one actually scales up to larger data sets. You can usefully navigate data sets of over 100,000 nodes. It still has the same weakness about you'd never want to use a method like this if you care about distance judgments. And even though you saw a bigger neighborhood, you could still get lost when the graph got big enough. So my next system was kind of a direct result of trying to solve the problem of if the graph gets big enough, you could get lost in these systems. I wanted to build something where you never would get lost. You'd always have a sense of where you were. So my next system, called Tree Juxtaposer, was specifically aimed at biologists who needed to compare trees side by side. And those trees might actually get to be quite large. So I'm going to start out by showing you a demo. I believe we're here. Is that right? Ignore the errors behind the curtain. It's just a little bit of Java nonsense. So one interesting thing here is if you're trying to compare the structure of these trees, let me actually turn off something useful as an example. If you just have to stare at these trees and I tell you that they are similar but not identical, and it's your job to figure out exactly how they differ, it's actually a hard problem, even if you're allowed to have some support like mouse over highlighting where what's shown on one side is also shown on the other. So we can start to see, well, wait, there's some difference here. Fulvaria and Carthamnus are down here, but oh, it looks like there's still actually siblings, so maybe the problem is somewhere downstream. So you can go through and try and mark pieces of structure and understand, well, is what's contiguous on one side still contiguous on the other? And then we can start to find, here's what's happened. This tree branch down there ended up getting moved over to here in this version of the tree. So you can start to understand that structure. So one of the tasks we were supporting in this was understanding these differences between trees. The part that I turned off, which is normally turned on, is automatically computing exactly those spots in the tree where there are differences on both sides. Now, the part I mentioned about navigating without getting lost, right now, this tree is actually not so huge. So it's possible for me to make one part larger or smaller and have the rest compress accordingly, but it's nice and it's nifty, but I'd argue it's not critical. Now, if we try and look at a larger tree, a couple things become more obvious. First of all, why you want an automatic algorithm to find the structural differences in the trees. Here's a case where these are two trees that have been reconstructed from the DNA of the species themselves, rather than, and there are two conjectures that are equally likely, given the data that the biologists at hand. You can actually get back many possible trees that you then have to understand the topological structure of and compare. One of the things that's nice about this kind of stretch and squish navigation is instead of just having a single focus, like with the hyperbolic stuff, you can have multiple foci where you look at the tree in more detail. Now, this idea of taking parts of it and stretching it and other parts being compressed accordingly is not a new idea. The part that's new, that's about trying to scale this up to large data sets, is the idea that says, let's say that we'd gone into here and looked at Arabidopsis, and we wanted to mark that. So let's make a colored mark here. And then let's say that we'd also gone in, explored some other part of the tree by some biological thing I don't know, but it looks like it's related to saccharin. Yeah. Now notice, one of the yeasts. So mycoplasma, sounds mushroomy. The thing to notice here is I'm making these little marks that are showing me some kind of a visual path through my data set. Notice how even though I might have compressed very highly a lot of leaves into one region, I'm still actually drawing these little colored blobs to give me visual landmarks of where I've been. So one of the aspects of the system is that it actually scales up to trees of more than 1 million nodes, and you can interact with it at 30 frames a second with this guaranteed frame rate interaction. But these little visual landmarks will always be drawn. Even if it doesn't have time to draw the whole data set in a single frame, it'll make sure to try to maintain these visual landmarks so you have some sense of, oh, I see, the purple stuff is beneath the green and the red and so on. So this kind of graphics infrastructure to preserve visual landmarks and have fluid interaction is something that I think is really important in scaling up to big data sets. So this question about if you've got these marks, is it worth bothering to draw them? After all, they're just small colored blobs. With a small data set, if you mark something, it's easy. You just draw it in the color of the mark, and you can see it. As your data sets get bigger and bigger, the possibility that some mark that has important semantic meaning might not be visible to you, that gets to be highly probable. For example, if you can freely move your camera, the mark could just be completely outside the viewport. One of the reasons we're doing this kind of stretch and squish navigation where it's as if the borders are nailed down is so that nothing can actually be off screen. It could be arbitrarily small on the side, but it's not going to be completely off screen. Or if you're allowed to have a full 3D way of drawing these, then one mark could be hidden behind another. This kind of rubber sheet navigation has a semantics of being 2 dimensions, even though you couldn't do it directly on a piece of paper, but at least it's not 3D, so you can't have occluded marks. Now, the tricky part about when marks could be invisible is if they're smaller than a pixel. So smaller than a pixel is something that's very common in a graphics card. If you're playing a game, things that are sufficiently far away, you just don't draw. You let the graphics system cull them out. In contrast, those marks might actually be really meaningful in this kind of visualization interface, even if they're quite far away or quite small. So we need a bunch of graphics infrastructure to try to do a smarter job of culling than just throwing everything away. The nice thing about this approach is instead of having to do some kind of a brute force complete search, you can know if you don't see a mark, it truly isn't there. So it can try and make the task of navigating to understand the structure more easy. So this approach actually does scale up to millions of nodes, and not just from a graphics point of view of the algorithms, but from a perceptual point of view of actually understanding what the picture means. We've got this idea that we guarantee marked nodes being visible, and you can have multiple areas of focus. Now, yet again, all of these kind of distortion-based approaches aren't going to work well if you have to do something where distance estimation really matters. Now, a lot of tasks where you're drawing trees, you just care about topological structure, like this is connected to that. It doesn't necessarily matter exactly how far away it is, although for some biological tasks it does matter. And of course, having this infrastructure that guarantees that these marks stay visible does require some infrastructure, although we've got a paper published last year that goes into the details of how to do all this efficiently.